Hello everybody. So in the last modules we have looked at some descriptive ways of describing our numbers, and we went all the way from the basic stuff such as looking at what types of numbers we have, um, to describing central tendencies, how do our data gather around the middle. And then finally, we have been looking at measures of dispersion. How spread apart are the data? Once we realize how close they are to the middle, looking at the mean, median, and mode, then just to get a clearer picture, we wanted to look at within those descriptive numbers, how far apart are they actually spread? Do they all gather around the mean, median, and mode? Or are they kind of more flat if we were to look at a bell curve? So those are all things that we've been looking at. In this module, we're going to start moving toward getting to some statistical analyses and so forth. And the first thing we need to do in order to get there is we need to take a basic look at probability. And within this, we're going to look at some basic rules for elementary probability, and we're going to look at some probability distributions, and we'll understand what all that means by the end of this module. So our goals for this module are kind of robust for those of you who are not familiar with math as much, but don't let that worry you. We're going to take a step-by-step process through here. So number one, we want to relate a statement of probability to a relative frequency distribution. Number two, we want to learn how to use elementary rules to determine the probability of the occurrence of an event. Number three, we want to recognize mutually exclusive events, what that means. We want to recognize what independent events are. We want to translate probability of occurrence to odds. We want to distinguish between what combinations are and what permutations are. We want to calculate the number of combinations and permutations of R things taken in at a time, and we'll understand what those mean. We want to compute the binomial probabilities by enumeration of sample space, by the examination of terms of a binomial expansion. We will understand that, I promise you. And we want to apply the characteristics of the normal curve to determine the probabilities of classes of random variables. So that sounds like a lot, but we will get through it. So when we're talking about probability, let's get a baseline of what we're saying here. This is the inferential branch of statistics that includes the study of randomly occurring events and outcomes of experiments. So how often is something going to happen? The probability that an event will occur is expressed in a fraction or decimal, and it is always between 0 and 1. 0, the event will not occur. 1, the event will definitely occur. And basically everything we're going to look at is things that come in the middle. So some basic definitions here. A set or collection of all possible outcomes of a probability experiment is called the sample space. So if I were to flip a coin, the one coin one time, my sample space would include a spot for head and a spot for tail, because those are my two possible outcomes of my experiment. And we will use flipping a coin a lot in here to give you some simple things that you can connect with. The sample space for our experiment is no launch, and successful flight. So what I mean here is, let's take a hypothetical experiment. Let's say that you are in a science class and you want to launch a rocket that you have built with your students in class, what is the probability, given previous success rates, the weather, and so forth, that you will have a successful launch on Saturday? So, in this case, our sample space is the experiment will not launch. We won't launch it. We will launch and have a successful flight, or we will launch and not have a successful flight. That is our sample space. Those are our three outcomes that we could possibly have. Any particular outcome, so one of these three, is a simple event. So these three events make up our sample space. Okay? So when we're talking about experiments, think about the things, the possible outcomes that you could have. Each individual outcome is an event, and all your events put together is your sample space. Now, some of this we'll see is easy to do when we have small numbers, but what if we have large numbers? Then it becomes a little bit more complicated, and that's when we're going to get into the second part of our presentation. So some probabilities are known from given facts: flipping a coin, rolling a die, or choosing a card. And what we mean here is when we flip a coin, you only have two possible outcomes. It's either going to be heads or it's going to be tails. When you're rolling a die, you have one of 6 possible outcomes, assuming you're using a normal die. And when you're choosing a card, you have one of 52 outcomes. Okay, or maybe you're going to divide it up into black and white, and so now you have 1 in 26 outcomes. However you divide it up. Maybe when you're rolling the die, you're going to roll even numbers. Now you have 3 out of 6, or 1 in 2 outcome, 1/2 there. Okay, so these are all called a priori probabilities. In other words, we have given facts before we start our experiment. We know what our probabilities are, and this we call a priori. Other things are not known until we actually do the experiment and get sufficient information to determine the probability. So for example, if I say, if I want to talk about driving to work, okay, and say that driving to work, what is the probability that I can drive to work in 15 minutes? Whereas in our a priori examples, our a priori probabilities, we had all the givens known. Here there are a lot of things that I do not know that could change the time that it takes me to drive to work. It would take several attempts to get the necessary information to determine to make a determination of the probability of getting to work in 15 minutes. The experiments would determine the relative frequency that I get to work in 15 minutes. So maybe over a month, I could look and see how long it takes me each day to drive to work over a month. And within that, I could determine the relative frequency as we have looked at in the past. And then from that, I could start to look at the probability of me being able to get to work in 15 minutes. This type of probability we call an empirical probability. Okay, and this is mostly what we will be dealing with in real life. For most of our samples here, we're going to be dealing with a priori probabilities, simply because it's easy to understand when we have those given facts. Another example of empirical probability that we hear all the time is the chance of rain. A 40% chance of rain means that under similar atmospheric conditions, it has rained 40% of the time in the past. Okay, so that's looking at that relative frequency when all these things align. In the past, it has rained 40% of the time. If it does actually rain, then we call this a success. Okay, so that's a key term that we will need to remember when we're looking at probability is success and the lack of success or failure. So this is some basic things that provide us with the background. The first half of this presentation, I want to go over 7 rules for you for probability. And these are pretty straightforward, but I want to explain them as we go through. Okay? So suppose that you are in a school and you want to select one random at-large representative from the student council. There are 180 seniors, 121 juniors, and 150 sophomores in your school for a total N of 450 students. So you want to select one person at random out of the 450 students. Rule number 1. The probability that an event will occur when the event is one of a set of equally likely events is 1 divided by the total number of events in the set. Written out, this means the probability of success is equal to the proportion of 1 divided by n. So our probability of success, P parentheses S, equals 1 divided by n. So what this is saying here is that when the event is one of a set of equally likely events, that the probability is simply 1 divided by the number of events. In our case, we have 450 students, and every student has the same opportunity of me selecting their name out of the bag. So that's what we mean when we say the event is one of a set of equally likely events. Then we can simply divide 1 by 450, and we get 0.002 or 0.2% chance. We can multiply it by 100 that any single individual will be chosen. Okay, that's rule number 1. If I'm going to roll a die or flip a coin, then I have an equal chance of getting heads and equal chance of getting tails. So I have 2 possible outcomes. My chance of getting head would be 1 divided by 2 because I have 2 outcomes, or 50%. Okay? That's how that rule works. So pretty straightforward and simple. Rule number 2. The probability of an event cannot exceed 1 or be less than 0. And that's what we say here. Where the possibility of S, PS, is greater than 0, greater than or equal to 0, but less than or equal to 1, where P of S, P parentheses S here, is the probability of success. And earlier we said if it's 0, it will not happen. If it's 1, it will happen. So somewhere in the middle we're going to get a fraction. So this rule defines the range of values we have in probability. And we've already said this rule. But for example, the chances of drawing an 8th grader out of our sample is 0. Because there are no 8th grade students in our set. Okay? The probability of drawing a high school student, on the other hand, is 1. Because all the students in our set are high school students. The probability of drawing a senior then is going to fall between 0 and 1, and we will look at that. So that's rule number 2. The probability of success is somewhere equal to or greater than 0, but equal to or less than 1, somewhere in that range. Number 3. If there is more than one event that could be considered a success, the probability of occurrence of any one of the successful events is the frequency of successful events divided by the total number of events, where F is the frequency of the successful events and N is the total number. Now that sounds like we're starting to jump off into the deep water here, but we're not. Rule number 1 said everything being equal, if everybody has an equal chance to win the event, then the probability of one individual would be 1 divided by the total number of n. Here we're simply saying if there's more than one event, then we simply divide the total possibilities of success by n. That's what the frequency is, the frequency of success. For example, if we wanted to pick a senior out of the 450 students, we know that we have 180 seniors, so we just divide 180 by 450. 180 is the frequency of successful events, choosing a senior. 450 is our total number of students. So our probability is 0.4, or a 40% likelihood that we would select a senior to be our at-large representative. So see, we're not in the deep water at all yet. We're barely getting our feet wet. Rule number 4. The sum of probabilities of every possible event in a set of events is equal to 1. And we write that as sigma p parentheses e equal 1, where e represents a simple event. So from rule 3, we can see that this is actually very accurate. So rule 3, we said it was a 0.40 or 40% chance that we would select a senior. Let's look at our other classmates. Sophomores, we have 150 sophomores over n, according to rule 3 of 450. That gives us a 0.33 or 33% chance of choosing a sophomore. The juniors, we had 180 divided by 450. That gave us 0.27. Got an extra decimal in there, but 27% chance of selecting a junior. And then we had the 40% senior. So if we add those together, the sum of all possible events is equal to 1. And that's what we have. Okay, so we're still barely getting our feet wet on this stuff. Rule number 5. This is going to be a very logical step from what we have already looked at. The probability that an event will occur is equal to 1 minus the probability the event will not occur. So P equals our probability of that the event will occur. 1 minus Q. Here Q is the probability the event was not a success, okay, or it was a failure. So if we look at our seniors then, we said that the probability of choosing a senior, according to rule 3, was 180 divided by 450, or 0.4, 40% chance that we would choose a senior. Rule 5 says the probability an event will occur is equal to 1 minus the probability the event will not occur. 1 minus 0.4 equals 0.6. There is a 60% chance then that a senior will not be chosen. Okay, that's simply what we're saying here. So again, we're still pretty shallow into the pool here. Okay, the probability the event will occur is equal to 1 minus the probability the event will not occur. All right, moving on to a little bit more. These are generally stated as odds. Oh, this is an important thing here. Okay, so this is one of our module goals. So when we're looking at odds, this is what we're looking at. So a junior or a sophomore chosen would be 270 over 450. So we're adding the total number of juniors and sophomores together. This would be equivalent to saying 180 over 450, which represents the seniors, to 270 over 450, which represents the sophomores and juniors, everybody else. Okay? So if we reduce those fractions, then what we have here is 2 to 3 odds that a senior will be chosen. This means that out of a large number of experiments, 2 would result in a senior being selected, and 3 would result in a junior or sophomore being selected, not elected. We're not electing anybody. But that's how you come up with odds in looking at probabilities, okay? You take the probability that something will happen and put that with your colon read as 2 against the probability that it won't happen, okay? So 180 over 50 to 270 over 45, there's 2 to 3 odds that a senior will be selected when randomly drawn out of the bag. Okay? So that's how we take probability and put it into odds. So we don't just look at the probability of something happening, we have to look at the probability that it won't happen. And using rule number 3, when we put those together with rule number 5 here, that's how we get odds. Okay? Rule number 6, the addition rule of probability. This rule, the addition rule of probability, is used in a situation S in which statisticians must compute the probability that at least one of 2 events will occur. So what we mean here is this. If J and K are our 2 events, then their respective probabilities are the probability of J and the probability of K. Okay? So we saw earlier the probability of S, success, for our single event. Now we're looking at 2 events, okay? And we want to look at the probability that at least one of these 2 things will happen. So the probability that either or both is stated as P, J, and K is equal to the probability that J will happen plus the probability that K will happen minus the probability of J and K, where the probability of J and K is the probability that both will happen. We're just looking for one, okay? So we're starting to get a little bit deeper into the pool, but we're still on the shallow end. Let's look at an example here. Consider the probability of a selection at random of a junior or a senior, okay? So before we were looking at the probability of just one class being represented, like the senior class came out to 0.4, 40% probability. Now we're looking at the probability of one of 2 different events happening. And here we're asking the question, what is the probability of a junior or a senior being selected? So again, looking at our formula, the probability of J or K equals the probability of J plus the probability of K minus the probability of both J and K. So when we put numbers to this, we see the probability of a junior, 120 over 450, plus the probability of a senior, 180 over 450, minus the probability of both of them, and we input a 0 here, okay? The 0 results from what we call mutually exclusive or mutual exclusivity, because we're only selecting one person here, and that person cannot be a junior and a senior. Therefore, they are mutually exclusive of each other, and we're going to subtract 0 from that. Because remember, what the question we're asking is, we're going to select one person, and what is the probability that this person will either be a junior or a senior? And since it's only one person and that person cannot be both, then the probability that both J and K, that this person will be a junior and a senior, will happen is 0. And therefore we call these mutually exclusive of each other. So what we end up with then is simply 300 over 450 minus 0, or 2/3, or 0.67. So we have a 67% probability that we will select either a junior or a senior out of the class. And if you go back to rule number 1, or it's 2, I believe, that talks about the set, that's what we set here, okay? So let's take a little bit more of an exploration of this rule of addition here. Suppose the probability of drawing an ace from a deck of cards 52 cards in the deck, 4 suits. The probability of drawing an ace then would be 4 over 52, or 1 over 13 if we reduce, or 7 or 0.076, or a roughly 7.5% chance that you would draw an ace. The same is true for drawing a jack, drawing a king, drawing a 2. If we're just drawing one card out of a typical deck of 52 cards and 4 suits, then the chances of drawing that one card, no matter the suit, is little more than 7.5%. What is the probability then of drawing either an ace, a jack, or a king on the first draw? So now we're asking ourselves, what is the probability that out of those 52 cards we will draw either the ace, an ace, a king, or a jack? So our rule of addition say we need to add together each of these things. And so 1 over 13 plus 1 over 13 plus 1 over 13 equals 3 over 13, or 0.23. You will draw one of the 3 cards your first attempt 23% of the time. And again, these things are mutually exclusive because what we left off from the formula is all events happening. We can't have all events happening because we're only drawing one card. So that becomes 0. So that's why we left that piece off the formula here, okay? So 23% of the time, you will draw one of these cards. So consider non-mutually exclusive events. So these are all mutually exclusive. Let's look at non-mutually exclusive. What if you were to flip 2 coins? What is the probability that one of the coins will land on heads? Okay, so the possibilities are the possibility of J is heads. We can call J heads here. The possibility of one coin is 50%, 1 out of 2. The possibility of K, again, tells, 1 out of 2. The possibility of J and K becomes 1 out of 4. Because here, when we look at our sample space, we see, if we're looking for, we want to see that both coins land on heads. When we look at our sample space here, we actually only see that 1 out of the 4 chances that we have here, both coins landed on heads. And so therefore, the possibility of J and K both happening, landing both coins on heads, is 1 out of 4. Our formula then is the possibility of either J or K is equal to the possibility of heads plus the possibility of tails minus the possibility of both heads and tails. And when we put our numbers in, the possibility of either J or K getting heads is equal to 1/2 plus 1/2 minus 3/4, or minus 1/4, or 3/4, or 75%. In other words, we're saying that if we flip 2 coins, there is a 75% chance one of the 2 coins will land on heads. The options are not mutually exclusive in this example because we have 2 completely independent experiments, and just because the first one might land on heads, the second one does not have to land on heads. When we create our sample space here, what we have to do is list all the possible outcomes that we could have. So that's what we've done here. When we flipped coin 1, we got a head, and coin 2, we got a head. We could flip coin 1 and get a head, and coin 2 and get a tails. We could flip coin 1 and get tails, 2 and get heads, and then get tails for both. So these are all the possible outcomes, and that's how we were able to get these numbers of 1/2, and 1/4. Okay, so these are non-mutually exclusive, or these are independent events, and so our odds change slightly when we look at these types of events. So Rule 6 is a little bit trickier, and again, this is our addition rule of probability. So now let's look at Rule 7. And for Rule 7, we're going to take a step into the deep end. Not very far, but we're going to go into the deep end a little bit. For those of you who are not as in love with math as you should be. And I refuse to say you can't do math. You just haven't been exposed to it in an adequate way. Rule 7 is just like Rule 6, except we're going to multiply. So the addition rule works when one wants to understand the probability that at least one of two or more events will occur. What if one wants to see the probability that all events will occur? For this, we have to examine the multiplication rule of probability. And in order to understand the multiplication rule, we first need to look at two things: joint probability and conditional probability. So we're going to come back to rule number 7 in just a minute. Okay, but let's first of all understand what joint and conditional probability are. So, joint probability. This is the probability of a joint occurrence that two or more events will occur. For example, what is the probability you will roll a die and flip a coin, and then the coin will come up heads? Okay? So we're looking at the probability of two independent events. Hence the term joint probability. So these are two independent events. One is not associated with the other. If we roll the die, it doesn't matter what we get. It's not going to have any influence on flipping the coin. So our chances then, if we were to write out each event and put it in a sample space, our joint sample here would look like this. Okay, what I've done is I've combined the roll of the die with the possible flip of the coin. So we could roll a 1 and get a heads. We could roll a 1 and get a tails. We could roll a 2 and get a heads. We could roll a 2 and get a tails. Roll a 3 and get a heads, and so forth until we get down to the end. Or you could roll a 6 and get a head, and a 6 and get a tail. Okay? So what we see here is that there are 12 possibilities, and the chances of any single event, according to Rule 1, is 1 over 12. Oops, wrong button. So the possibility of rolling a die and getting any number and then flipping the coin and getting heads has now come down to 1 over 2. Because this is the consequence of the independence. Okay? It doesn't matter what we roll on the die. The flipping of the coin is still completely independent of rolling the die, and it becomes 1/2. Okay? Consequently, we could say, what is the possibility or probability of rolling an even number and then flipping the coin? Okay, rolling an even number again, that gives us 6 out of the possible 12 because we have not determined what our coin needs to be. So the possibility of rolling a die and then being able to flip a coin and get either heads or tails is also 6 out of 12, or 1/2. But let's say, so that's joint probability, okay? Now we're going to look at conditional probability. And in conditional probability, we're going to say, what is the probability that I could roll an even number and then turn around and flip a coin and get heads? Okay, so you can see how we're changing our rules a little bit. And so we're putting conditions now on the events. And so therefore we're moving into this conditional probability. Technically, this is the occurrence of two or more events with conditions applied. Again, what if we said roll a die and get an even number and then flip a coin and get heads? Now we have conditions for our two independent events. So our formula that we have here looks like this. And don't let these formula freak you out or anything, okay? It just explains what we're doing. So this is read as the possibility of H given D, that bar that looks like half of an absolute value is given D, is equal to the possibility of H and D divided by the possibility of D. Okay? So in other words, the possibility of getting an even number, given that we have a coin flipped on heads. Actually, we'd probably look at it the other way. What is the possibility of getting heads on a coin, given the fact that we roll a die and get an even number? That is equal to the possibility of H and D, that upside down U is just read as and, divided by the possibility of D. So let's put some real numbers to this so we understand what we're saying. The possibility of H given D, this can be read as the number of elements or events in H and D, or the number of ways H and D can occur. So in our table then looks like this. We can roll a 2 and get a heads, roll a 2 and get a tails, roll a 4 and get a heads, roll a 4 and get a tails, and roll a 6, get a heads, and 6 get tail. The possibility of getting an even number becomes 3 out of 6. Okay? The possibility of getting heads becomes 1 out of 2, or half. Now let's go back to our rules. So these are the possibilities we could have gotten out of our 12 possibilities that we saw earlier. So we're looking at getting heads. Rolling an even number is 3 out of 6. Getting heads on the coin is 1 out of 2. So let's look at our rule. We said toward the bottom here, if one wants to see probability that all events will occur, then we look at the multiplication rule. So instead of adding like we did in Rule 6, we're going to multiply our results. So the possibility of getting an even number is 3 over 6, or 50%. The possibility of getting heads is 1 over 2, or 50%. So what we get here then is 3 over 6, or 1/2, times 1/2, which gives us 25%. So rule number 7 says that there is a 25% chance that we will roll an even number and then flip heads on our coin. Okay? So those are the basic rules of elementary probability. Let's look at a couple of other things here. We're not going to go into great detail here, but I want to introduce you to these terms. Like I said, we're not going to go into detail because it really is outside the scope of what we're doing or the purpose of our class. But the first one is Bayes' theorem. This theorem is used when there are various other events to consider in making probability estimations. We're not going to review this, but I wanted to give you an example of what it would look like and let you know that there are really many, many more layers to statistics than what we're doing. But for the purpose of our course, we're just looking at the very basics. But consider you have a student body that is 47% male, 53% female. Then think of the change to student rules. Okay, so let's say we want to change the student rules where it is known that 40% of the females and 30% of the males support this change. An anonymous editorial has appeared in the student newspaper in support of this change. Given the fact that we have 47% male and 53% female, and that 30% of the males support the rule, and 40% of the females support the rule, what is the probability that the anonymous writer was male? Okay, so you can see here how this really doesn't apply to those basic rules that we were looking at. And so in order to answer this, we would use what is called Bayes' theorem. Okay, but we're not going to deal with that in the scope of our work, so we're going to move on from that. I just wanted to give you an example, and in fact there's a whole level of statistics called Bayesian statistics. Alright, so methods of counting. This is kind of the last thing before we move into our next section. It's kind of wrapping up those rules and starting to move into the next section of our presentation, looking at probability distributions. So we've discussed that probability is expressed as the relative frequency of the class of events that we consider to be successes. Okay? When we flip a coin, if we're looking for heads, then when it's a head, it's a success. When it's not a success. And we can plot those and put them on a relative frequency table. This can be expressed as a fraction, with the numerator being the number of successes and the denominator being the total possible outcomes, or our successes plus our failures. Okay? So we're simply looking at the ways that we count our successes. So the fraction, if I flipped it 5 times and 2 out of the 5 I got heads, then my success rate would be 40%. 2 is my numerator, and 2 plus 3, 2 wins, 3 losses as my denominator. Counting these types of possible outcomes can become cumbersome when we get into large numbers. In statistics, we use what are called permutations and combinations to help with these more complicated numbers. So we're going to take a minute here and look at what we call permutations and combinations. We're going to see here that n exclamation point, this is read as n factorial, is equal to n, whatever our number is, times n minus 1, times n minus 2, times n minus 3, until we get to 1. And this will make perfect sense to you. If it doesn't right now, I promise you. Where n is a positive number. For example, 3 factorial would be 3 times 3 minus 1, which is 2, times 3 minus 2, which is 1. That's what we mean when we said ... 1, when our n minus whatever gets to 1, we stop. So 3 times 2 times 1 is equal to 6. So 3 factorial is equal to 6. Another example, 5 factorial would be 5 times 5 minus 1. So 5 times 4 times 5 minus 2, which is 3. 5 minus 3 is 2. 5 minus 4 is 1. We stop. So 5 times 4 times 3 times 2 times 1 equals 120. Okay? So 3 factorial equals 6. 5 factorial equals 120. By definition, and we're going to see this in a bit, 0 factorial and 1 factorial both equal 1. Okay? So those are the basic things that we need before we can look at what permutations and combinations are. Just understand what a factorial is. It's that number multiplied by each number before it, where that number is a positive integer, and that 0 factorial and 1 factorial both equal 1. So with that, let's look at permutations. Suppose that you have 3 events, and we're just going to call them W, X, and Z for short. How many ways can you combine these or be arranged? This is called permutations. Okay, so we could say our events would be WXY, WYX, XYW, xwy, ywx, and yxw. This is 3 factorial, and we saw earlier that 3 factorial is equal to 6. Okay, so what if we wanted to take 2 events? So the little r is our event at a time, the total number of events that we have, and r is the events that we want to take at a time. So our formula then becomes 3 factorial divided by n minus r, so a total of 3 events minus the number we want to combine, 3 minus 2 factorial. And so what this tells us is that while we had a combination of 6 different events when we were looking at all 3 of them, if we were just looking for a combination of 2 events, then we still have 6. And our sample space would then cover wx, wy, xy, xw, yw, and yx. Okay? Oops. So let's talk about what this means here. Let's put this in real terms. Suppose you are a basketball coach and you have your 5 starters and you were asked to rank your top 3. How many ways could you choose the top 3 players? So let's look at our formula again. So 5p3 means that we have 5 players, 5 events, or 5 total players. The 3, the subscript 3, means that we want to pick 3. Okay? So our formula then asks, our question is, how many ways can you choose the top 3 players? So we're ranking them 1, 2, and 3. So, you know, think of your 5 players. We could have a guard, the center, and a post. We could have guard 2, center, post. We could have guard 1, center, forward. You know, lots of ways you can do. When we look at the formula, there are actually 60 ways that we can take 5 players and choose the top 3 of them. Okay, and the key here is that we're ranking the players. That's what a permutation is. It tells us the possibilities that we have when we're looking at numbers and we want to rank. On the other hand, what if the coach were just asked to choose 3 players and not rank them? When we deal with permutations, we saw the ranking of the top 3 players out of 5 could have a possible 60 rankings. What if the coach were just asked to pick 3 players out of those 5? The formula here then changes slightly. Let me show you the permutations formula again. Here's our permutation formula. N factorial over quantity n minus r factorial. Our combination formula is n factorial r factorial times the quantity n minus r quantity factorial. So again, we have 5 players and we're looking to just choose 3. We're not asking to rank them, we're just looking to choose 3. So when we start plugging in our numbers, we now see that we have 120 numerator. Our denominator is now 12, which equals 10. Player choice combinations such as 1, 2, and 3, in this instance, is considered the same as 3, 2, 1, and 2, 3, 1. Therefore, if we don't rank the players, if we're just going to choose 3, we have reduced what our permutation of 60 was where we ranked them down to 10 where we have chosen them. Okay? And that's the difference between permutations and combinations. So permutations is adding a ranking order out of a set, combination is just looking at a set of numbers, and within that set, we're going to not have any duplications. Okay? So with that said, let's move into the last part of our presentation, and this talks about probability distributions. So probability distributions, this is what we're talking about here, and you can see this is building on what we just said. If we had three newlywed couples, and let's say they were discussing the possibilities that each of them would have a son as their first child, what are the possible outcomes that this could happen? Here we see the possible outcomes, and we've lined them all out here. So we can see that one outcome would be that they all have a son as their first child. The last outcome would be that they all have a daughter. And in between, we have 6 other outcomes. So there are total possible outcomes of 8 when we're looking at this. Okay? But what if instead of 3, we just looked at 3. What if instead of 3, the group were joined by 5 more newlyweds? And now we had a total of 8 couples. How many different outcomes for a first child would that generate? So here it's a little bit easier to manage because we only have 3, but what if we had 8? So to understand how to do this, when we're getting into these larger numbers, we're going to take a look at these 3 things. We're going to spend the most of our time looking at binomial distributions. We will spend a very short amount of time looking at normal distributions and see how it falls with the normal curve, and then we'll look at the Poisson distribution in passing at the end, because we're really not going to deal with that again. I just want to introduce you to that. So, binomial distributions. This is an important slide here dealing with properties and characteristics. So experiments have 3 properties in common. An experiment has a sequence of independent trials. For each trial, only 2 outcomes are possible, and a particular outcome has the same probability of occurrence for each trial. I'm going to explain and give you examples of all that, okay? These characteristics imply that any trial event does not influence the outcome of any other trial. The population is divided into 2 groups, whatever the term groups resemble. And either the population is very large or samples are drawn and replaced in the population before the next sample is chosen. So let's take the fact that we have 8 couples now, and we want to see the probability that each of their firstborn child will be a son. So the properties then, a sequence of independent trials. So each of those is independent. They are not reliant upon the other. Each trial has 2 outcomes, so success and failure here would be a son or a daughter. Particular outcome has the same probability of occurrence for each trial. Each couple has the same probability that he or she, or they, will have a son. So the characteristics imply these following things then. Any single trial does not influence the outcome of any other. We have 2 groups, and the population is very large, or samples are drawn and replaced in the population. So this is getting into how we get sample populations, but for the sake of what we're doing, let's say that this is a representative sample of our population. Any experiment with these properties and the implied characteristics then is called a binomial experiment. In a binomial distribution, S, as we have already seen, equals success and is considered to be a random variable. It's random because any chance of success of any particular trial is random and determined by individual outcomes. The success of couple A having a son is not determined at all by couple B having a son. Okay, so this is what we're saying here. That's why we call it random. it has the same possibility with every individual trial. The probability distribution for success provides the probabilities of success, or S, for various values. Another name for this distribution is called the binomial distribution. The parameters for success are N and Q. I'm sorry, the parameters for success are N and P times the quantity of Q, where N is the number of trials, P is the success, the probability of success, and Q is the failure. Okay, one coin toss would be seen as P equals Q, or 1/2. Okay, so the probability of success of getting a head is equal to 1/2. So let's take flipping 3 coins and wanting to get heads on all threes. On all three. This is a true experiment, a binomial experiment, because it falls within those characteristics that we saw earlier that we said a binomial experiment had to have. Particularly a sequence of independent trials, only 2 outcomes possible for each trial. It's how we define success and failure. And a particular outcome has the same probability for each trial. So when we look at our sample set here, we see the possibilities here of getting trial 1. We flipped the coin and got a tell. We labeled that Q. That was not a success. Trial 2, got a tell. We would label it Q, but I didn't want to label everything. In trial 3, we got a tell. So our possible successes here was 0. We go through the second line. We get a head, a P for a success, tell, tell, possible S, or possible success 1. And we can go down through there until we get to the point where we have heads, heads, heads. Our possible S at this point becomes 3. Okay, so let's take this information now and look at what the probability, can we determine what the probability of getting exactly 2 heads or 2 successes would be. And we can see just the possibility of getting 2 heads appears 3 times. What is the probability that that will occur? When we look at our sample set here, we were able to tally up, again, 3 coins, and we're going to flip them, and out of 8 times, we were able to get 2 heads. The possibility of getting 2 heads out of 8, we can see here, was 3 times. So our success then of getting 2 heads is equal to 3/8, or 0.375 maybe. Is that what 3/8 is? When our n is small, this is very easy for us to figure. Remember, the first child being a son had the same sample space as with the example of the coin. Okay, so when we're talking about small sizes here, these things are easier to figure. And we can look here, this distribution represents what we saw on the first child being a son. The success being 0 in all daughters was 1 out of 8 times. The success of being 1, where we had 1 son and 2 daughters, was 3 out of 8. The success of 2 sons, 1 daughter, was 3 out of 8. And the success of having 3 sons, S equals 3, was 1 out of 8. And just to verify, let's pull that chart back up. And here it is. So you can see that only 1 out of 8, if we were to add a success column out here, this would have been all 3 success. and this would have been 0. Okay, so 1 out of 8 was our success rate for 3 couples having their first child to be a son. Also notice the denominator is the possible outcomes for an individual experiment. Here we have 2 to the nth power, where we have 2 outcomes for n trials. So we have 3 trials. 2 cubed equals 8. That is the total possible outcomes we have for each experiment. So if we were to have, we said earlier that we wanted to have 5 more couples join. So our total possible outcomes, instead of being 2 to the 3rd equal 8, would be 2 to the 8th, because we have 8 possible experiments. Instead of only having 8 columns, we would end up with 256 different ways of stating the possible outcomes for 8 couples instead of just 2. So our binomial distribution then, we said success of 0 having no sons was 1. There's only 1 chance that we'll have no heads in our sample space. Oh, and we're back to flipping coins, not children, I'm sorry. Check to see the math, and we saw that with the same with the child. Okay. So the chances of having no success is 1 out of 8. We are working with combinations here. Remember our formula for combinations. So we can put this together and read that 3 chances or 3 combinations that our flip is equal to 0, in other words, no heads, is equal to 3 factorial, which is 6. And we just carry the math out. 3 factorial equals 6 for our numerator, and the denominator is 0 factorial, which we said equals 1. By definition, we have to make this equal to 1. And then within the parentheses, 3 minus 0 is equal to 3. So 1 times 3 factorial equals 6. So in other words, we have 6 over 6, or 1, for the chances that we do not get any heads on our experiment. This can be carried out for all possibilities. So if we were to change the success that we would get 1 head, then we would just substitute those numbers in, and instead of 0, we would have 1 here, and we would carry that out through the total set of 3 to see what the chances are that in 3 experiments we got all of them. The formula then for the binomial distribution is the possibility of success, P over S, is equal to the number of trials in the number of combinations and the number of successes over 2n, where n is our trials, S is our success, and C is this formula we just did, the combination formula. Okay, that NCS at the top is our combination formula, and we divide that by 2n, or 2 to the nth power. Let me promise you, you do not have to memorize this. I just want you to get the big picture of what we're doing here and why we're doing it. Earlier when we said that 256 different combinations, if all 8 couples were to have a child, the probabilities that the first one would be a boy, we could plug that information in here, and instead of 3, we would have 8. So these numbers, instead of 3 factorial, it would be 8 factorial, and what we would end up with would be a very small chance that all 8 couples would have their first child as a boy. We could do it visually if we were to create a sample size that large, but for 256 different outcomes it might be a little cumbersome. So that's why we go to these formulas, okay? So the binomial distribution formula is your formula for combinations divided by 2 to the nth power, where n is the number of trials that you have. Let's see an example here. So let's say John has a true-false test with 6 questions. John is going to flip a coin for each question and wants to know what is the probability he will get 5 questions correct by flipping a coin. Again, our formula is the binomial distribution, where the possibilities or probability of success is equal to combinations over 2 times n, where n is the number of trials. S is success and C is combinations. So in our formula here, we're going to plug in our numbers where we have 6 trials. In this case, trials is equal to our tests, test questions, 6 test questions. And we want to get 5 successes, so our success is 5. So we're going to take all this over 2 to the nth or 2 to the 6th power, because again we have 6 questions or 6 trials, and we want to see the probability that John can randomly flip a coin and get 2 questions or get 5 questions correct out of this. So when we look at our combination formula, then our n is going to be our number of trials. And again, that's n is the number of questions. So each one of these is an independent experiment. Think of it like that, as an independent experiment, where it doesn't matter if he gets question number 1 right, he still has an equal opportunity to get question number 2. So each of these questions is an independent experiment. And then 5, the R here represents the number of successes that we want to have. Okay? So when we do the math here, 6 factorial over 5 factorial times the quantity 6 minus 5, which is 1 factorial, so 5 times 1 factorial, we end up with 6 over 64, or 0.09, or the probability that John will get there's a 9% chance that John will get 5 answers correct out of 6 by simply flipping a coin to determine true or false. What if the test instead had multiple choice questions, and instead of only 2, there were 4 possibilities now? What is the probability that John will answer 5 correct by randomly guessing? So our formula changes slightly here, and we can see that n is the number of trials, in our case test items again. P is the probability of success for any experiment, for our case guessing the correct answer. S is the number of successes we want, in our case 5 correct answers. Q is the probability of failure, in our case chances of guessing wrong, the opposite of P. And R is the total number of successes and failures in our trial. In our case, we have 6 questions. So when we plug our numbers in, we see that 6 times the quantity 1/4 to the 5th power, so P to the S here turns out to be 1/4 to the 5th power, because you only have the probability of success is 1 out of 4, and our success rate is 5 out of 6 questions, so that's why we have 1 P to the S is 1/4 to the 5th, times the quantity 3 over 4 to the 1st power. So Q is our possibility of failure. So we're going to fail 3 out of 4 times, and then R minus Q, or R minus S power, is the total number of successes and failures and trials, in our case 6. So we have 6 trials minus 5 successes is 1. And when we carry out all this math, what we come out with is 0.004, or less than a 1% chance that John can guess on a 4-item multiple choice test where there are 6 questions, and he will get 5 of the 6 correct. Not going to happen. Okay? So that's a binomial distribution. And it sounds a little complicated. We're a little bit further in the pool, but we're not at the deep end. But that's the hardest that it gets. Okay? Normal curve, pretty straightforward here. The normal curve gives us an insight into probabilities. Remember this when we continue our studies. We've looked at the normal curve. Your last assignment, you were looking at the probability that somebody in the United States, a random male, would be taller than I am, standing at 5'6". Okay. And so forth. That's how we can use the normal curve or the normal distribution to anticipate probabilities. And the last thing we're going to look at here is what's called the Poisson distribution. And we're going to go through this very quickly. This distribution is used to figure probability of events that occur rarely over a period of time. So you can see that we've changed our parameters a little bit from binomial. Now we're looking at things over time. For example, the number of plane crashes in a year, the number of droughts that hit a state in a decade, the number of phone calls received by the secretary during the first 3 hours of school. Mathematically, what we're looking for is the rate of lambda events, how often an event happens per unit of time, and the Poisson distribution provides the probability that x will occur k times during a unit of time. Again, you're not going to be asked to memorize this and regurgitate it. This is truly for your information to just let you see that we're only touching the surface. The biggest thing here is looking and understanding that binomial distribution and how permutations and combinations fit into figuring out probability. So some more examples then of the Poisson distribution. How many raisins are there in a slice per slice of raisin bread in a given number of loaves? How many cars on the highway pass a certain point every minute? You know, how many misspelled words are there in a large textbook? These are things that we would look at, and we're not looking at how many there are, we're looking at the probability that these exist. Okay? So our formula looks a little crazy, don't get worried. The probability of x equals lambda k, where k is the number of times the event is that we wanted to look at, that happened within a unit time, lambda to the k power times e to the negative k, and e is going to be a natural logarithm here, and it's always going to be a set number, 2.71828, over k factorial, or lambda k over k factorial times e to the negative k power. Sounds like a lot. Let's look at what this actually looks like when we do it. Given the school operator receives a mean call of 3 calls per minute from 7:30 to 9:30, what is the probability that on any given day she will receive exactly 1 call, 4 or fewer calls, or more than 4 calls? So if we look at this formula and plug in our numbers, we see that we have the probability of one call is equal to about 15%. We're not going to go through this formula, but you can see our lambda is 3. Our k is the number of times the event happens, and here we want 1 time. And our e to the negative k, we carried out, we're going to get 15%. Okay, there's a 15% probability that she will receive 1 call if her average is 3 calls for those 2 hours. Then you can see we carried out the others. So, again, we're not going to go through that. That's just for your information. So let's look at the goals of what we had at the beginning of this presentation. So we wanted to relate a statement of probability to relative frequency, and we were able to do that. We wanted to use elementary rules to determine the probability of an occurrence of an event, and we looked at 7 rules. Spent more time on the 7th rule, the multiplication rule. We wanted to recognize what mutually exclusive events are. This comes in when we're talking about permutations and combinations. The same with independent events. Translate probability of occurrence to odds. This came in with our rules as well. Distinguish between combinations and permutations. Calculate the number of combinations and permutations of R things taken in at a time. Compute the binomial probabilities by enumeration of sample space. by the examination of terms of the binomial expansion and apply the characteristics of a normal curve to determine the probability or probabilities of classes of random variables. So this is to give you this background on probability, because this is going to play a huge role when we start looking at our statistical analyses and results, and that we need to understand probability when that comes up. And so you have some simple assignments that just touch the surface of what we're looking at here, just to get you again familiarized with these terms. So best of luck on that, and when we come back in the next module, we are going to begin somewhat of a rather lengthy journey looking at inferential statistics.